request for number 28 first, and then we'll look at number 24. So it looks like we're focusing in on intercepts. 28, symmetry. We didn't actually talk about symmetry in this chapter very much, maybe not at all, but we have talked about symmetry before. In fact, we probably should have applied it to this chapter. Remember how origin symmetry is where if you turn it upside down it still looks the same? Okay, so is there origin symmetry for this function? One way to test for symmetry is to plug in a negative x and see what answer we get back. Do you remember the testing for odd and even functions? So origin would be asking if it's an odd function, would be kind of the question. So what we do is we plug in a negative x and then see if we get the opposite function out of it. So let's blow this up just a little bit bigger. Okay, so I'm going to go negative 4 times negative x over negative 5 times negative x squared plus 14. So the negative times the negative on the top gives me positive 4x. And on the bottom, the square turns that negative positive, because a negative x times a negative x is a positive x squared. The negatives cancel. So then that negative 5 keeps the bottom negative. So all that's changed is the negative that was on the top is now gone. Doesn't that mean that the entire fraction has changed in value from negative to positive or whatever, right? Isn't that true? That that's switched because of that negative is now missing, right? So the negative there, see how this negative and that negative, it makes it so that this answer is the opposite of the original, yes? And so that verifies that it is in fact odd or origin. I don't think there are any.
Is it because it's the same with the difference?
It's the opposite. Like it's the entire same function, but like multiplied by a negative. Yeah.
So if you plug that into the calculator and just turn it upside down?
Yeah, if you look at the graph and it's the same upside down as it is right side up, then it's, yeah. And you could sketch the graph to verify it, to show me your work. Okay, number 24. To find x intercepts, all you do is numerator equal to 0. So we go x plus 9 equals 0. So there's an x intercept at negative 9 comma 0. Because of that. Yeah, well, x intercepts, you set the numerator equal to 0, so those two are the same. But for y-intercepts, you have to plug in x equals 0. So it's slightly different. Y-intercepts, you plug in x equals 0. Y-intercepts, you set the numerator equal to 0. What else? Okay, did I hear a request for 29? Was that what it was? Okay. So you'd rather have 31 than 29? Okay. 31, you have to find the critical values. So to do that, you take the numerator and set it equal to 0, and you take the denominator and set it equal to 0. That gives us x equals 7, which is an x-intercept. And that gives us x equals negative 6, which is an asymptote. Then we split the problem into intervals from negative infinity to negative 6, from negative 6 to 7, and from 7 to infinity. Notice how everything is parentheses because all the intervals are open due to the fact that there's no equals, right? So then we choose a number to test in each interval. Those are my suggestions, but you could choose anything that would work within those intervals. Then you plug them into the problem. So like negative 7 minus 7 is a negative 14. Negative 7 plus 6 is a negative 1. That gives us a positive answer. Plug in 0, we get negative 7 over positive 6, which gives us a negative answer. 8, we go plug in 8, so 8 minus 7 is 1, and 8 plus 6 is 14, so that gives us a positive answer. We're looking for answers that are less than 0, which means the interval that would be negative answers. So therefore, the solution for this problem is from negative 6 to positive 7, because that's where we get a negative value from. Yes. Okay, then there was something else that I heard. Can't remember what it was. Okay, is there a different issue in 32? Because it looks very similar. Your critical values would be negative 12, positive 9, and positive 1. 1 is an asymptote, so that has to have parentheses around it. But the other two are intercepts, so since it's equal to, they are brackets. Set up your intervals and then test each one to see which ones in this case are positive. The last one was negative because it was less than. This one's positive because it's greater than.
How do you find a hole?
A hole in the graph happens when it's not in the domain in the original problem, like it makes the denominator 0, but then that thing cancels with a what's the word I'm looking for? Factor on the top. So like if there was an x minus 1 on the top and the bottom so that it would cancel out, it would be a hole instead of an asymptote. That's not going to happen very often.